Hello everybody, welcome to Unit 3, and in this lesson we're going to be covering arrays. And arrays in C++ follow the same concepts and principles as they do in Java. So you should be able to use arrays in C++ after getting a few syntax specifics, which are covered in Chapter 8 of the book. And we'll cover that briefly, but then we'll also practice array processing and explain how to pass arrays into functions in this lesson. We'll also look at the sizeof operator and see how we can use that with arrays. So by the end of this lesson, you should be able to declare and use arrays, pass arrays to functions, process individual or multiple array elements, and of course finally use the sizeof operator to calculate declared size of a local or global array. And we'll get into that. So as a refresher, arrays are a structured data type that back many of the abstract data types that you find in the containers of the standard template library. So we declare arrays like this. We indicate the type followed by an identifier and then the size in brackets. The size declares the maximum number of components or elements that the array can store. So in this case, we set the max size to 10, but we are only actually storing 5 here as in this chart. Okay. A key consideration is that the elements are stored in contiguous or adjacent memory space. So that means that the values that we have stored are actually right next to each other in memory. And so you can see, like Java, we can access the elements using the array subscripting operator, or index operator as it's also known. So here you can see in order to get the values of the 0th element, right, we just put the 0 in the brackets just like we would in Java and many other languages for that matter. Additionally, we can initialize the arrays with values when it's declared. So you can see here we can declare it like this where it's not initialized, and here we can actually give it values when we first declare the array. So you can see that these values are translated down here. Again, this is just like Java. And in this example, we can see a simple test of our basic array operations. So here we have our main method and we're declaring our list of 5 elements, and we're just going to loop through them using a standard for loop and an index of operator. And then we're just going to send it out to the output stream. So if we run it, this is the result that we would see. We would get 0, 5, 10, 15, 20, right? No brainer. But here's one difference from what you might be used to. If we were to accidentally change our for loop processing, if we said, I want to go from 1 to 5 instead of 0 to 4, as you can see here, and we output it, what do you think would happen? Well, in Java, you would get a index out of range exception and the program would halt. But with C++, we get this weird value here. Okay, so why do we get this weird value in C++? Well, let's take a look. If we execute the program in debug mode and set a breakpoint at our for statement, and you can see that right here, and trace its execution, you will see the array list and its 5 elements at index 0 through 4. So down at the bottom in your debug window, you can see your variables, and so here you can see that our array list is at this memory location, and here's the contents of it. So again, this is our memory location. If we look at the memory using our debug memory window, which is a tool that you can access, we can see their values in memory. And inside of the memory during execution, you can see that this location stores the first element. You can see that this is memory location 010FF87C. Well, that matches what this says right there, right? And you can see that it stores the value of 0, right? We've got 0, 0, 0, 0, 0. Right next to it, which would be list index 1, storing 5. And be aware that each element is an int and it occupies 4 bytes in memory, right? And these values are in hexadecimal, so each byte is 2 digits. So we got a byte here, a byte here, a byte here, and a byte here, right? And you can see that this is our memory location. So we went from 87C to 880. Well, C in hexadecimal is a decimal value of 12, So if we add 4 bytes to 12, we get 16. And 16 in hexadecimal is 10, right? Because hexadecimal goes from 0 to 15. So this is basically just like carrying a digit over in decimal math. We got to 16, so this goes back down to 0, and we add 1 to the next place. Now, next in list would be list subscript 2, or list index 2, which is going to store the value of 10, right? You can see 10 here. Well, A in hexadecimal is 10. So we're storing 10, and then we've got 3 extra bytes that are empty. So again, just like math, we carried our tens place over, or well, it's not a tens place because we're not in decimal, but we carried our place over, and you can see when we went from this memory location to this memory location, we added 4 bytes, so we went from 88.0 to 88.4, okay? And you can see that list 3 stores 15. Again, F is hexadecimal for decimal 15, right? And you can see that we've added 4 bytes. And you can see that list subscript 4, list index 4, we went from 8 to C, so we went from 8 to 12, okay, because we added 4 bytes. And you can see that it is storing the hexadecimal version of 20, right? Because again, this is the 16s place. So we've got 1 16 and 4 ones, which equals 20. Now, the memory location after list 4 doesn't belong to this array, but it's a valid memory location and may hold anything. We don't know what this is going to hold. Now, in debug mode, it's going to do certain things to the memory, but in general, if we were just executing this, we wouldn't know what's going to be in this location at runtime. One interesting thing to note that when we're looking at memory like this, we have to be aware of 2 things. First is the concept of Endianness. And this is a reference to the book Gulliver's Travels. And it referred to how they were an egg, how you've got a little end and a big end, right? In our case, this refers to how data is stored in memory. And there are 2 ways. You have a little endian and a big endian. In our case, we have a little endian, which is kind of backwards from how we would normally think about numbers, right? The number is broken up into 4 2-hex digit numbers that we've seen already, where the least significant bits are written to the lower address spaces, and the most significant bits are written to the higher address spaces, or the higher blocks of memory, as you can see here, right? In this situation, we have a little endian, and here is our 32-bit integer stored in hexadecimal format, right? And you can see that our least significant digits, right, go to the lower location in memory, right? So we've got OD, OC, OB, OA. Now, the big endian, you can see that these are written the same way. This is, imagine this being a number that you would normally read from left to right. You can see that the most significant digits are lower in memory, and the least significant digits are higher in memory, because these are our memory locations. So if you look up here, you notice that our digit 5 in our array, you know, our first index, not our 0th index, which was 0, but our second index, or first index, was the number 5, right? Well, you can see that it was 5, and then the next byte, and then the next byte, and the next byte. So this is the least significant digits, followed by the next group, followed by the next group, followed by the next group. Again, here's 10, right? So 10, followed by 0, 0, 0, 15, 0, 0, 0, and then 20, 0, 0, 0. Another interesting thing that you need to be aware of is that of something called 2's complement. And if you notice, when we printed our 5th index, okay, which was position 5, not 4, you saw that we got the number negative 858993460. But if we look at memory, we see that the value stored in memory was CCCCC, right? You can see that right here. This is where that value was stored. So what's up with that? Well, if you think about it, we don't have negative signs for values in memory, right? You don't see anything representing negative values here. So how do we store negative values? Well, there's a couple different ways to do this, but in our system here, we use what's known as 2's complement. And when calculating 2's complement values, while it's outside of the scope of this course, we can use some tools at our disposal to see that this is in fact the case. So here I've used an online calculator to convert our values CCCCC into binary, and then use the online calculator to find what the 2's complement was. So you can see here that our value is the same, right? So this was our binary version of our hexadecimal CCCCC, and if we convert it into 2's complement, you can see that that value is right there. So we're taking the reverse of it. We're taking the 2's complement representation, converting it into a decimal value, and you can see what we get. So again, this is outside the scope of the course, but I kind of wanted to take a moment to help you understand what's going on, why we see these values, and why we get this negative value here. It's also important to note that the junk value that you get that's displayed depends on how you are compiling and executing your code, as well as what OS you're using and what compiler you're using. So there's a lot of different things that can be displayed. So for example, in Visual Studio debug mode, this is what I get, right? I get the negative 858993460, or what was stored in memory was CCCCCCCC, right? If we switch it from debug to release mode, you'll see that we get a different value. And if I run it on the Linux subsystem in Windows using the G++ compiler, you can see that I get a different number, right? You can see 32767, right? And when I run it on my Raspberry Pi using the G++ compiler, which is a different version, you can see that I get 5. So it just depends on which compiler you're using, and we're not going to dig into all of that. Again, it's outside the scope of this class. But the lesson here is that an index outside of the value from 0 to the size of the array minus 1, right, is an invalid index. And it's a logic error to access an array with an invalid index regardless of what value will be returned or what compiler you use. Okay? So due to compiler differences, you may get different results with this segment of code. And the C++ standard specifies index out of bound will lead to undefined behavior. So once again, this is a logic error, and you should just not write this kind of code. With Java, you get a little bit of protection, and it automatically throws an error for you. C++ is based on C, and that says, hey, you're the programmer. You know what you're doing. I'm not going to try to stop you from doing that, because maybe you have some legitimate reason for doing that. Okay? So it's just something that you have to be aware of. And this type of error, an off by 1 error where you go past the index 1's position, is very, very common, and it can lead to, that's what they say, is undefined behavior. So just be very careful when you're using loops and make sure that you are stopping when you know you should be stopping. Now, one of the things that we have in our toolbox to help us with going outside the bounds of an array is the sizeof operator. And this returns the size of a variable in bytes. Okay? So given this code fragment, what do you think is going to get printed out with the size of these various things? Okay? Well, you can pause the video if you want and figure it out. Or on my machine, okay, the size of a double is 8 bytes. So that's going to print out 8, right? And the size of this array, right, which is an array of doubles, okay, and we have 20 of them, so that means it's going to be 8 times 20, right, or 160. And because of that, this expression in the third cout, this line here, is often used to find the declared capacity of an array, which is declared locally or globally. And this is key. It's got to be a local or global variable, variable. And in this case, you can see that if we take the size of array and divide it by the size of the type that it is storing, right, that will give us how many elements that we have to process, right? So there's 20 elements in this array, right? And of course, the textbook has more information on the sizeof operator, so you can look up in Appendix G and you can see how it's listed as an operator. Okay, it is in fact an operator. So with it being an operator, how do we know that it's an operator, not a function? This looks like a function to me, right? It's got the parentheses and all that. Well, it's completely legal syntax to omit the parentheses. Okay? So I could say size of double, size of array divided by size of double. Okay? But the problem with this, and why we often use it with the parentheses, is just because of order of operations, right? You have to be very careful on what gets executed first. Okay? It might try to take the size of array divided by the size of double. All right? So that's just, it's just safer to use the parentheses to make sure that your order of operations is considered in the way that you think that it should be handled. So one of the most common things to do with an array is to loop over the contents to retrieve their values. Okay? And you can use a for each loop to do this array traversal. So you can see here, unlike the previous examples, which we use the standard for loop, here we're using the for each loop to iterate through the items. So we have an item for our integer item in our array, right? Do something, right, involving this local variable. Okay, so here, item, we're going to iterate through the array each time. It's going to get the value of the index in the array and store it in item. So it's going to go to array 0, array 1, array 2, array 3, array 4, right? And each time, item is going to hold a new value, and then we're going to do something out with it, right? So in this case, you can see that we declared an array of size 20, and we only initialized the first value. So this is going to print out 5 with 19 zeros. Okay? Now, there are some caveats to this approach. Like Java, you can only retrieve the value and not modify it, right? That means that the for each loop can be handy if you only need to read each element in their stored order, and you don't need to use the index in any way. Additionally, the for each loop only works for a local or global array. And we're going to see why in the next section of this unit, but it's only going to work for a locally declared array. So if we are inside of a function and we create an array, then you can use this for each loop. Okay, if you're passing an array into a function, you're not going to be able to use it, and we're going to see why in a little bit. And by in a little bit, I mean the next slide. So let's explain why the only local or global array part using this example. Assume that we have this 5-element array declared in main, and main calls the find max function and passes this list into the function. All right? And inside of this function, we use a for each loop to process this array parameter. Right? This will not compile. Okay? And that's because, as we stated already, the for each loop can't be used with a array parameter. So here we have R is our array, and we've passed it in, like here we've declared it as list, and we're passing it in, right? This will not compile because we cannot do this, right? But why is this the case? Well, when an array is passed into a function, we are only passing in the address of the first element and not a copy of the entire array. Inside of the function, this array parameter is not an array. It is a pointer, which is a variable that stores a memory location. And I know this is very confusing because you're like, but we're passing in an integer array right here. Well, that's the syntax, but this array, this ARR, is actually a pointer. All right, and we're going to talk more in depth about pointers in Unit 4, but this is to point out that you cannot use a for each loop inside of a function that takes an array as a argument, as a parameter. Okay, and since a pointer is not a container like an array, right, this for each loop isn't going to work. If we change the code a little bit so it compiles, we can observe this behavior. Okay, so inside of this function, this array is this array parameter again is not an array but a pointer, which is a variable storing a memory location. Okay, so here you can see the memory location of list when we examine it inside of main. Okay, If you continue debugging, we can examine the array inside of our test function. And you can see that its type is int star, which is int pointer, okay, right here. You can also see that if I take the address of the first element and store it in the pointer variable, it has the same memory location of our array and our int array. All right, so here you can see that this is our list, and you can see the memory location of where its first element is at. Okay, here you can see that this is a pointer because it says constant int star, and you can see its memory location. And here you can see I create a pointer, and I take the memory location. This ampersand is the address of operator, and you can say, give me the memory location of the first element in this array, and you will get the same value for all three things. Okay, again, don't worry too much about the syntax here. We're going to cover this in Unit 4. I'm just showing you all this so you can understand that when you pass an array into a function, you can't use the for each because it's not actually an array when you pass it in. It's a pointer, okay? So it's not an array anymore, but it's a variable storing a memory location, okay? And this will be explained more in chapter 12. And again, because it's not a container type, the for each doesn't work, okay? I think I've said like 4 times now, all right? So when you're doing your homework, you've been told. Of course, this concept applies to the sizeof operator as well. Since an array is passed as a memory location, the sizeof operator won't work with an array parameter in a function. And here you can see our original size of test, right? Or R in this case. And inside the function, right, the size of that array is 4, which is the size of the pointer, right? So here we've passed it in. It is now a pointer, not an actual array, and the size of this pointer is going to be 4 bytes, okay? And then if we divide 4, the size of array, by the size of a double, which is 8 bytes, we get 0.5. Of course, since we're doing integer math, we don't have decimals, so it's going to truncate it, and we are left with 0, right? So again, the sizeof operator only works on local and global declared arrays. I mean, you can use the sizeof for any variable type, but if you're trying to get the size of the array using this algorithm right here, hey, give me the size of the array divided by the size of its contents, that will tell me how many elements I have. It only works in a local or globally declared array. Of course, another common thing that we do with arrays is we sort them, okay? I cover quite a few different sorting algorithms in Cs225, at least the basic ones, but their algorithms are the same no matter what language they are implemented in. So as a refresher, we're going to take a look at a couple sorting algorithms. So to start with, let's take a look at insertion sort. And as a refresher, it maintains a sorted region at the front of the array, and it sorts by inserting items into the sorted region, right? So here we have, we're going to loop from the second position, right, index 1, until the end of the array. We're going to find where in the first part of the array it fits, okay, and then we're going to insert it. And that's the algorithm. And you just move down the end of the array, keep putting it back into the previously sorted spot, all right? So here is a more concrete version of the pseudocode as well as the actual implementation in C++, all right? So if we were to run this program here, you see we've got our arrays 5, 10, negative 3, 20, and 2, right? And we execute this, we will see that our list is going to go in the following way, right? So we're going to start at 1, and we're going to look to see that it's in order. So 10 comes after 5, so that's already in position. Next, we're going to come down to 3, or the second element, right? Index 2, the third element, really. And we're going to sort negative 3 into the already sorted portion of the list. Well, is -3 less than 10? Yes, so we're going to move it up. Is -3 less than 5? Yep, so we're going to move it up, right? And then we're going to come down to 20, which we're going to do the same thing, but it's already sorted, so it doesn't go anywhere. And then we're going to look at 2, and we're going to see that, hey, 2, you need to move all the way up to the top, and so it's going to go all the way up to the top, well, not less than -3, and then we're done, right? So here for I, which is 1, right? Because if you remember our pseudocode, we started at the second element, right? While it's less than the size, right? Which is equal to size minus 1, right? We're going to store this value, whatever thing that we're pointing at, our index, our marker, right? We're going to store it in a temporary array, right? And then we're going to work our way backwards through the array, right? And we're going to shift things down, right? If it's less than, okay? So while j is greater than 0, so while we are somewhere before the front of the array, and the array at the position before us is greater than our value, right? So in this case, right here, let's take a look at -3, right? While we're not at the beginning of the array, and while the value of the one before us is greater than our value, which is stored, which is -3, we are going to move this into the previous position, right? And we're going to increment it down. So the array at j is equal to the array at j minus 1. So we're going to take 10 and move it down, keeping in mind that -3 is stored temporarily, right? So then we're going to see, okay, well, then we're going to move up 1, and we're going to say, okay, well, is 5 greater than -3? Yes. So then we're going to execute this again, and we're going to move it down 1. And then we're going to get here, and we're going to say, oh, we are not greater than 0, so we're going to go ahead and drop it in. Okay? So that's the algorithm in a nutshell. And we can look at again in this and actually in execution. So let's take a look at what's actually happening in the code. So here you can see I've set a breakpoint at my insertion sort method, or function, excuse me. And so I'm going to go ahead and start the debugger. And I've got the memory window open, so you can see right here, you can just pull up debug, windows, memory, and select memory 1, okay? And you can choose which columns you want to see, and you can specify different memory locations, but we want to go ahead and, so right now we're stopped here at our call to insertion sort, all right? We haven't actually gone into the call yet. You can see we've got our array, and it's got the memory location there. And so let's go ahead and pull this up in the memory viewer. So if we type in 009DF920, which is our memory location for our array, right? You will see the contents of the array stored there. You can see here we have 5, right? 5. You can see that we have 10, right? So 0A, that's hexadecimal for 10, right? -3. Here is -3. All right, this is, remember, this is stored in 2's complement. All right, so -3 is really, you're counting down from your highest number. So in this case, we've got FED, so -1, 2, 3. So that's what -3 looks like stored as 2's complement. All right, then you can see 20, right? Well, we've got 20 right here. All right, hexadecimal 14 is equal to decimal 20. And then here you can see that we've got the value 2, right? 2. So if we step into this function, you can see here we are now at our call to insertion sort, and you can see in our local variables down here, you can see we have our integer pointer array, okay? That's our memory location we declared right there. You can see j is a junk value because it hasn't been assigned a value yet, right? And temp is stored as 5 for some reason, and size is 5 because we passed that in, right? So if we continue going down, all right, now you can see that our temp value has changed to a junk value. And so if we continue executing, right, so now temp is, we haven't actually executed this yet. If we continue down, all right, temp is now our value of 10, okay? which, if you recall correctly, was what the value of our array at position 1 was. So right here, this is now stored in temp. Okay, and if we continue, right, we haven't done anything. We completely skipped this while loop because 10 was not less than 5, right, which was the value before it. All right, so we're going to keep going, and now we've incremented, and now we're on I2. So we are on the 3rd position, right? And we are going to set J equal to that 3rd position, right? And now we are going to check to see, is J greater than 0? Well, yes, it is, because J is 2, excuse me, the 3rd position. And our array at J minus 1, right? So J minus 1 is going to be our 2nd position. And we're going to see if that is greater than temp, right? So if it is, we're going to enter the loop. And it is, so now we're going to take the position at J and store the value at J minus 1 into it. So remember, J is 2, so at J minus 1, we're going to be accessing the 1st index, okay? So we're going to be taking this 10 value, right? And we are going to be storing it in the 3rd position. So we're going to be moving it down 1, right? So if we go into that, you can see here that the value in memory changed, right? You can see it was copied. That's what we just did. We took this value and we shifted it over 1 position, right? Well, we went this way with it, right? And so if we continue, right? So now we are doing the same thing, and we're checking to see if that value is the same, and it's true. So now what are we going to do? Well, we're going to shift. We've gone up 1 level, so now J is 2. So now we're looking at position, or excuse me, J is 1. So now we're looking at the position of index 0, and we're going to be putting it into index 1, right? So we're going to see this 5 get copied into this position. So if I go to the next step, so you can see that's what happened, right? And then we're decrementing J, and we're going to move on. And now we're going to check that again, and we're like, nope, that doesn't pass because we are at index 0, right? J is 0, J is not greater than 0, so we skip the while loop, and now we're going to store the value of temp, which is -3, into this 1st memory location. So you're going to see this turn into FC, FF, FFFF, right? So if we execute that, boom, you saw the memory change, and that's what happened. Okay, and it's going to continue doing that as we work down the line, right? So now we're going to look at this 20, and we're going to see if it is less than 10, and it's not going to be, so we're going to skip all of that, right, and move on to the next segment, which is going to be looking at 2, and see if 2 is less than the one before it. And if it is, you're going to see all these values up here change. So you can see we were going to shift 14 down, we're going to shift 10 down, we're going to shift 5 down, right? So if we watch the red, you can see that those values change, right? And now we're going to pop 2 in where this 5 is, because that's the insertion sort algorithm. So again, this goes a little bit beyond what we cover in 219, where we're actually getting into the memory and we're showing you the actual memory contents changing. So I just thought that this was kind of cool, and this is something that you can do, and it really helps you to understand what's going on inside the box instead of just, you know, magic. And if we actually run the program all the way through to the end, you'll see that we actually get the result that we're expecting with the array being sorted after we call the insertion sort. Now, I'm not going to go into the same level of detail for selection sort that I did with insertion sort, but its algorithm is pretty simple. All you do is you start at position 0, and you go down the list and you look for the smallest value in the array. And when you find it, you swap it, those 2 values, and you move on to the next one. You start, and then you go from index 1 and you look all the way down, and you find the next smallest value and you swap them, right? And then you go to index 2, you look through the entire array and you find the smallest value, and once you're done, you swap them. And so you do that, and when you go all the way through, by the time you're done, by the time you get to the last index, guess what? You are guaranteed to be sorted from smallest to largest, okay? And you can do the opposite with, you could look for the largest and move it up That's just how you implement it. Okay, but that's selection sort in a nutshell. So now that you've seen insertion sort and we kind of briefly went over selection sort, be aware that these are very basic array processing techniques that are in these algorithms. Okay, very common. So like I said, I've covered the insertion sort, but at this point you should be able to take pseudocode and convert it into actual code to execute the algorithms that we're looking at, right? But I recommend you looking at these additional resources for additional help and kind of additional material to review. So chapter 18 covers searching and sorting algorithms, so that'd be a good resource for you. The standard template library array class, okay, talks about the arrays, and so you can reference those from cplus.com. And also the standard template library vector class, the vector class, which covers a dynamic array, which is very similar to the array list in Java. It's an array that can grow in size. Okay, so again, these are all great resources for you to go out and check out on your own to help you understand arrays and the different algorithms that are used in the various sorting algorithms. So as the final thing that I want to do, I want to take a look at a comparison between arrays in Java and arrays in C++, right? So it's helpful to understand the similarities and the differences between the two, right? So first, arrays are implemented in Java as an object, and as such you have access to a length property. In C++, they're implemented as pointers, which we'll cover next unit, but as such they do not have a length property, and we can use the sizeof operator to manually calculate the length of the array, or the size of the array, right? By taking the number, how much memory the array takes up, divided by the type of the unit that it's holding, right? And remember, this is in bytes, so that will give us how many actual, what's the max size of the array that it can hold. Okay, now if you want to actually track what's the declared size, like how much actually, or how many actual units are stored in the array that are legitimate data, right? Not just the max size of it, but useful information that's inside the array. You need to actually keep track of those things individually, okay? No language will do that. As far as the declaration in Java, they can be declared with any integer expression. It can be a constant or a non-constant, right? But with C++, you can only declare them as a constant int. So you cannot ask the user for input and use that variable that you read in an integer to create an array. It's going to give you a it's going to give you saying a warning that's saying you didn't use a constant integer to declare the array size. Okay. So what you can do is you can create a constant array or a constant integer based on the value that the user input, but you still have to do that step or cast it as a constant int. In Java, you can get an index out of bounds exception if you try to access beyond the array's bounds. C++, no such luck, right? You're just going to get a undefined behavior depending on the type of compiler that you're using. And so you have to be especially careful in C++ not to go outside of your array bounds. Okay. In Java, you can pass an array to a function and modify it. It's passed by reference, so what you modify in the array inside the function will come out. In C++, you're passing a pointer, right? So remember that our sizeof operator works differently. We're not getting the size of how much memory the array is taking up. We're getting how much memory the pointer to that array is taking up. All right, so that's something to keep track of. And then finally, we can return a array as a return type in Java, but we cannot in C++. If you want to modify an array, all right, you pass it in as a pointer and you modify the array, and then you can then use that same array outside of the function. All right, but you cannot return the array as a return type. So that's the similarities and differences between C++ and Java in a nutshell. hopefully this helps. I know it's kind of a lot to take in, but I recommend you definitely practicing with arrays before you get to the homework, just so you're more comfortable with using arrays in just very simple programs, right? Just create a function that takes an array in as a parameter and just do some processing with it, just so you're familiar with how to do that. So that brings us to the end of this unit, or this lesson. In summary, we looked at how to declare and use arrays in C++. And these concepts and principles are the same as they are in Java, but there's some minor differences that we've covered that you need to be aware of that can be a little tricky for first-time users. And you should be able to know and apply the basic techniques to process an array, to sort an array, and then pass an array into a function. These are all critical things that you're going to be using throughout the entire course. So I can't foot stomp this enough. You need to practice. If you're not comfortable using arrays in C++, you need to get there as quick as you can. Okay? So again, that's the end of this lesson, not the end of the unit. We've got 2 more lessons in this unit, and we're going to take a look at some things that involve arrays, strings or C strings, which are character arrays, and then in the 3rd lesson we're going to take a look at processing 2-dimensional arrays.